I have a 1/4 to. Let's come back here and continue. Okay. Okay. So we talked about the fact that the head and the base are are related to each other in terms of resistance to overturning. So I want to go through and sort of show you the overturning sensitivity of the stability sensitivity of rail to both vertical and lateral loads, or combined vertical and lateral loads. So the first case, I want to do 3 cases. I want to do the case where the load is on the center of the railhead. I want to do a case when the load is on the gauge side of the railhead, and when the load's on the field side of the railhead. So the vertical load. So we have a vertical loads. Let's start off with the case where the vertical load's in the center of the railhead and the lateral load is over is on the top of the railhead here. So the height of the rail is H. The base of the size of the base of the rail is B, and the width of the railhead is W. Okay. So if we do a sum of moments around this base over here, we would get L times H, which is the moment, the lateral load times the height there, minus V times the distance from here to there, which is the base over 2. Equals 0. So L over V, to prevent overturning, has to be less than B over 2 over H. So for UIC 60 rail, H is 172 millimeters, base is 150 millimeters. So L over V has to be less than 0.44 for the rail to maintain stability without a fastening system. With a fastening system, of course, it's going to be it can take a higher L over V ratio, but without a fastening system, it's fundamentally stable at L over V less than 0.44. Everybody understand what I just did here? You're awfully quiet. Everybody still there?
Yep.
Okay.
Yes.
Yes.
All right. So that's pretty straightforward. Okay. So now let's look at the case. Let's say we're on a sharp curve. So the previous case, by the way, this is the case where we tend to have on straight track. I drew the flange on the wrong side. No, I'll just drew the flange. So the head of the contact is down the center of the railhead, and then the lateral load will be actually at the center of the railhead as well, but again at a height H. The next case is if I have a curve and I'm actually flanging. This is the flanging case we talked about a couple of classes ago. Oh, where my vertical load now is over here. My lateral load is over here. Again, this is my H. This is my B. This is my W. And I want to look at overturning over here. So L times H minus V. Now the distance is this, which is B over 2 plus H over 2 equals 0. Or solving for L over V, to avoid overturning, L over V is less than B over 2 plus H over 2. No, B over 2, sorry. But, sorry, that's a W, not an H. I must be putting everybody to sleep. Not a person commented on that one. Divided by H. Let's do that so it's a little bit easier to read. Okay. So again, L V width of the railhead is W, width of the base is B, height is H, so L times H minus V times this distance, because we're overturning over this point. So this is B over 2 plus W over 2. B over 2 plus W over 2 equals 0. Prevent overturning, L over V is less than B over 2 plus W over 2 divided by H. Again, UIC 60 rail, H is 172, W is 74, B is 150. So L over V is less than 0.75. You notice that this is more stable than this case. This case was 0.44. This case is 0.6765. The third case where I have field side contact. Where do I get field side contact when my wheel is worn? I'm going to show you this a little bit later. If the wheel is worn, I can have contact out here. Again, H, W, B, overturning this point. That's my L, LH minus V. Now we're looking at essentially, okay, let me draw that better, because this drawing is so bad that it doesn't make the point. Okay, my V is here, my L is here. This distance here is now B over 2 minus H over 2. because that's B over 2, that's H over 2, that's B over 2 minus H over 2. So LH minus V times B over 2 minus H over 2 equals 0. L over V is less than B over 2 minus
Maybe from H, it's W.
You're right. Good. Good for you. I'm glad to see you're awake. Absolutely. Over H, this is W2. Right. So my L over V is now less than B over 2 minus H of 2 over H, put in my values, and it's 0.22. So you notice that if I have contact on the field side of the railhead, which I do get with worn wheels, then my overturning stability is actually less, and I have a greater risk of overturning. I also see this on the low side of curves, where I will have my contact on the field side, and I have the potential of overturning my rail on the low side of a curve as well. For UIC 50 rail, for center head contact, let me go back to the yellow one because for UIC 50 rail for center head contact, it's 0.41 as opposed to 0.44 for UIC 60 rail. So this is where the higher height comes in, because the rail base is actually the higher height and the smaller base. Does everybody understand what I just did here? Anybody have any?
So yes, I have a question. So if the H is bigger,
Yes.
so the L over V is smaller.
If the H is bigger, the L over V is smaller, right?
Professor, what is the L and V? The forces, the ratio between the forces?
Yeah, the L over V is the ratio of the vertical load versus the lateral load on the rail, that the wheel
Okay.
the rail. So what we're looking, just think of the rail with the vehicle on it. The vehicle is pushing on the outside of the curve. And
Yes.
we talked about wheel climb in a previous class, but you can also overturn the rail. I mean, if the force is if your lateral force is high enough, you're going to overturn your rail, right?
Mm-hmm.
So this is what I'm doing here, is I'm trying to show you what are the overturning forces would be without fasteners. Now, once I have a fastener, then of course I would introduce the restraining force of the fastener, and that would of course keep you from overturning. But what happens if you have a fastener that's missing? Which is what happens. So we do get overturning problems. So I just want you to understand that the stability of the rail by going through this exercise.
Understandable.
Okay. Now, rail life. We're going to spend a lot of time talking about rail failure in this class. We're going to talk a lot about the failure. But in broad general terms, I believe I introduced the concept of millions of gross tons already in this class. Does everybody remember the concept of millions of gross tons of traffic?
No, can you please repeat it?
Okay, good, because this is a very important concept. Okay, so the way we look at the life of a rail, you can't just look at the life of the rail in years, because if I have a very, very, very busy line and I have another line that sees maybe a train a week, 10 years of traffic on the two lines are not equal. And we see a lot of differences in traffic between busy lines and not so busy lines. So we talk about the life of rail in something called cumulative MGT, or millions of gross tons. So let's work down here. Let me go back to the pen. Okay. Let's say I have one train and it's a 1,000 ton train. Okay. 10 trains is 10,000 tons of traffic have passed over it. 100 trains is 100,000 tons of traffic. 1,000 trains is 1,000,000 tons of traffic is equal to 1 MGT. 10,000 trains, therefore, is going to be 10 million gross tons. And 100,000 trains is going to be 100 million gross tons. Now, how long it takes to get 1,000,000 gross tons is going to depend on how many trains that we have. So if I have, let's say I have a line where I have a train an hour, one 1,000 ton train an hour. So in a day, and let's say I run 20 hours a day, just because I want to make my numbers early. So one day sees 20 trains or 20,000 tons. In a week, I'm going to see 140 trains or 140,000 tons. In a month, I'm going to see 600 trains or 600,000 tons. In a year, I'm going to basically see 7 MGT. In 5 years, I'll see 35 MGT. And in 10 years, I'll see 70 MGT. Okay. Now let's say we're in the heavy axle load world for a moment, where one train is 10,000 tons. And 100 trains is now 1,000,000 gross tons. 1,000 trains is 10 million. 10,000 trains is 100 million. Okay, if I take a busy US freight line where I see 20 10,000 ton trains a day, so that's 0.2 MGT, right? 200,000 tons per day. In a year, I'm going to see what? 360 times that. So that's 360, 3,600, 7,000. So I'm going to see roughly 70 million gross tons a year in 1 year. In 10 years, I would see 700 million gross tons. So to put this in perspective, a medium density passenger, okay, a very light density rail line will be less than 1 million gross tons a year. A busy passenger line will be between 10 and 20 million gross tons a year. A busy heavy axle load freight line will be between 50 and 100 million gross tons a year. Does everybody understand now what million gross tons means?
Yes.
Yes.
Okay. I need you to be very clear on this because I'm going to be start using MGT very, very commonly in this discussion. So if you're confused or you don't even know about it, please interrupt me. This is a really important point. So now let's go back to talking about rail life and MGT. So you can see that for tangent or straight track, with modern maintenance techniques, my rail life can be as much as 2,000 million gross tons. Okay? So how long does it take me to reach 2,000 million gross tons? Well, if I come back over here and I go to a very busy rail line, 100 million gross tons a year, and there are lots of rail lines out there that are 100 million gross tons per year, certainly in the heavy axle load world. That's a 20-year rail life. If I had the same rail on this medium density line over here, which only had 20 million gross tons a year, then all of a sudden, I'm looking at a 100-year rail life, which is a long time. But under 100 MGT a year, that's 20 years. That's not that long. And that's on straight track. If I had a 600-meter radius curve, my life drops down to about 750 million gross tons, which in this 100 million gross ton a year operation is only 7.5 years. And even in a 20 million gross operation, it's still about 35 years. If I had a 200-meter radius curve, for example, in a metro, if I had a 200-meter radius curve, my rail life will be down to the order of about 100 million gross tons. Which means in a heavy axle load world, I'd be replacing that rail every year. And in a 20 million gross ton per year world operation, I'd be replacing it every 5 years. And there are a lot of metros out there that are between 10 and 20 MGT per year. So all of a sudden, the 200-meter radius curve on a metro, that rail may still have to be replaced in 5 to 10 years, which is a relatively short time for such an asset that you really want to live long. Now you notice, does everybody understand how I've described this so far? Is everybody clear on this discussion?
Yeah.
Any comments? Any questions? Okay.
Yes, why 100 million gross tons? Why 100? Why not 50?
Well, it depends how many trains you have. It all depends on how many trains you do. If I had one 10,000-ton train an hour and roughly 20 tons a day, I would be 70.
Okay.
If I had two 10,000-ton trains in an hour, I would be about 140. So if I have 30 trains a day, 30 10,000-ton trains a day, I would be 50. Remember the passenger case I gave you before, the 1,000-ton trains? Okay, but you run a lot. But you know, so if I have 5 500, if I have 50 trains a day, so let's take the Haifa Tel Aviv line, okay? How many trains a day run on that main line? You got one about every 10, 15 minutes, right? So you're probably running 4 trains an hour, 20 hours a day roughly. So that's about 80 trains a day. Each train's about 1,000 tons. So you're running 80,000 tons a day. So that would be 800,000. That's about 2.5 million gross tons a year. 365 times 365 times what did I say? 80 trains a day.
Yes, with
So
1,000 ton.
that would be about 30 million gross tons a year. If you were running 40 trains a day, you'd be running 15 million gross tons. If you were running 20 trains a day, you'd be running 7 million gross tons. So that's why when we talk about things like rail life, we can't talk about time and years, or really you can't talk about number of trains. We want to talk about MGT, number of tons.
Okay.
Alan,
Yes.
isn't the velocity matters?
The velocity measure doesn't, the velocity measure will come in when I calculate the stresses in the rail for failure. But when I talk about, when I talk about rail life, and in normal railroad terminology, when somebody talks about how long is a rail is going to last, I'm really going to say 100 million gross tons, 2,000 million gross tons, 500 million gross tons, and that's really velocity independent. For a while, the British Railways many years ago tried to come up with a concept of equivalent million gross tons, where they factored such factors in there as velocity, but it became so clumsy and so difficult to apply that nobody used it. It was just not a practical way to apply it. The velocity will enter when we talk about rail stresses. When we talk about fatigue life of rail, that's where it's going to come in.
Okay, thanks.
Now, one of the things I want to just point out very quickly here is the fact that you notice I'm showing that the rail life increased significantly between the 1980s and 2010. And that's because there were significant improvements in rail metallurgy, there was significant improvement in rail manufacturing processes, and there was significant improvement in rail maintenance practices, particularly lubrication and grinding, which we're going to talk about in this class. But nowadays, a good, well-maintained rail section should last between 1,000 and 2,000 million gross tons, or about 1 to 2 billion gross tons, if you want to think of it that way, on straight track. Curves, it drops down very quickly. Okay, so we talked about rail steels, so let's introduce the concept of rail steels. There are, in fact, 3 different classes of rail steels in common use. Standard, which is what you get if you don't specify anything else, intermediate hardness, and premium or high strength rail. They all weigh the same, but the difference is in the yield strength and hardness of the steel. The better the steel, the greater the yield strength, the greater the hardness, the more expensive it is. So typically, premium rail has about a 20 to 30% cost premium associated to it with standard rail. So you get 20 to 30% less premium steel for the same price, for the same amount of money as you would get for standard. Now within premium, there is head hardened, where the head itself is hardened, usually using some sort of heat treating or electric current process. There's a fully heat treated section where the entire rail section is treated. So in head hardened rail, only the head is hard. Everything else is standard. In fully heat treated, the entire rail section has a higher strength. Alloy steel, where we don't use a heat treating process, we use an alloying process, and we add alloy to the steel, and it affects the entire rail section. And then the fourth category is low alloy heat treated, where you use a combination of low alloy and heat treatment. And there are there are several dozen different types of premium steels on the market. Which you choose is really a function of the performance that you want to have, which performance you want to have, availability and price. Because premium steel also is often not as available as standard steel because it's in very high demand. So let's talk about the difference in properties. Standard rail steel has a yield strength of about 500 millipascals and an ultimate strength of 1,000 millipascals. So does everybody remember yield and ultimate? Let's just do a quick refresher. If I do a stress strain diagram, which is basically a load deflection diagram. So I take a piece of rail steel, make a cylinder out of it and pull it, and I plot the stress versus the strain. The curve will look like this. It'll be linear up until this point, and that's the yield stress. So the yield stress is the point at which the steel goes from linear to nonlinear. And then at that point in time, it plastically deforms. And then at some point, it actually breaks, it fractures. And where it fractures is its ultimate strength. So the yield strength, which is this point over here on the stress strain diagram, for standard steel is about 510 megapascals. The ultimate strength is about 1,000 megapascals. The elongation, which is the slope of this stress strain diagram, is about 10%. And the hardness of the steel is 310 BHN. Now, I should point out there are 3 different hardness scales, Vickers, Rockwell, and Brunel. So most railroad standards are written in terms of Brunel hardness, which is BHN. Sometimes you'll see someone in Vickers or Rockwell. There are standardized conversion tables. You can go from Rockwell to Vickers to Brunel. But for most places, for most of the time, the railway industry has standardized on Brunel hardness. And believe it or not, both UIC standards and AAR standards are both written in terms of Brunel hardness. So they're actually using the same scale in that particular case. So this is standard steel. By the way, to put things in reference, normal structural steel, the type you use to build buildings, is somewhere between 200 and 250 megapascals yield stress. So the yield strength of standard rail steel is better than double the, for example, in the US, we use what's called A36 steel. A36 steel is about 250 megapascals. So it's about half the strength of standard rail. Now, if I look at premium rail, the yield strength is up to about 800 megapascals, and the ultimate strength is closer to 1,200 megapascals. The elongation is still about 10% because we want to have that amount of ductility. And the hardness is up to about 370 BHN. So the hardness is about 60 points higher than standard steel. Here's a property comparison of various UIC steels. or actually, I should say various standards. Here's UIC, here's one set of EN standards. The BS is British steel, ARIMA is a US standard, and you can see we're looking at 800 to 1,000 as the ultimate strength. For the UIC steels, the ARIMA steels are a little bit harder. And this you'll see this pretty much throughout as well. You'll see the ARIMA steels are stronger. Here's the hardness. HB is Brunel hardness. Sometimes it's called BHN, sometimes it's called HB. So you can see the UIC standards are between 200 and, well, the EN standards, the UIC standards aren't listed here, but they're similar to the EN standards. They're between 200 and 300 for the standards, and then up to about 400 for the premiums, and that's where up to about 390 for the premiums. The AR standards or the ARIMA standards are about 310 for the standard, up to about 370 plus up to 400 for the premium. For those of you who are interested in what goes into the steel, I'm not going to spend a lot of time on this. If you're interested, I'll give you some good references, but you should see this in most steel manufacturers. Rail steel is considered to be a low carbon steel. So its percent carbon varies between 0.4 and 0.8%, depending on the strength. Usually the more carbon, the stronger the steel. There is manganese, silicon, phosphorus, sulfur, hydrogen, oxygen contents. These are maximum allowables in parts per million. These are all in percentages. What you'll find is there's a lot of commonality between the steels, but there's still some differences. So you can see UIC steel, the lowest grades of UIC are lower percentage carbons. Lower grades of the EN steels are lower percentage carbons. The ARIMA steels are a little bit higher percentage carbons. Before I go through the mill, I want to show you a little video on rail steel. Figures you deserve a break listening to me talk for a minute. So I'm going to let's see if I can find this video here and get it to work. Let me share sound. By the way, I should comment, this video is one of a series of videos produced by Network Rail, which is the British infrastructure owner. If you remember the discussion last time, Network Rail is the British infrastructure owner. They're all on YouTube. It's amazing what you can find on YouTube. I'll be showing some of them through the course, but I don't have enough time to go through all of them. I strongly recommend you browse through YouTube under the Network Rail, and they have some on rail, they have some on signaling, they have a whole range of nice videos. This one happens to be a nice one on rail that I use as sort of an introduction because it has a nice view of the steel mill and the chalk slot. If you should be able to hear the sound. If you don't hear the sound, please tell me. Otherwise, I'm going to assume that you can hear everything.
At Network Rail, we're responsible for over 20,000 miles of track, and that means over 40,000 miles of rail.
Notice he talks about miles and not kilometers. So I want you to point out to you that it's not just the crazy Americans who use the English system sometimes. The British use a hybrid because they'll be using metric for everything else, but they still talk about miles.
Rail has many advantages over roads. It's self-steering and faster. It's got a higher loading capacity, and most of all, it's safer. 15 times safer than travelling by car. And one of the main reasons it's so safe is because our maintenance teams and engineers put a huge amount of work and care into looking after it. The type of material we choose to make our standard rail from is very important and highly specified. It's a 0.6% carbon steel with other alloying additions to increase its strength and hardness. It's a high-performance material and as hard as a typical drill bit. 99% of our rail is made by Tata Steel in their huge steelworks in Scunthorpe. As a guide to the scale of the operation, the building containing the rail production line is over a mile long. The rail production process begins with 7.5 metre long blocks of steel called blooms, weighing 6.5 tonnes. These blooms are heated in a furnace to 1240 degrees centigrade to make the steel behave plastically and be capable of being shaped. The red-hot blooms are cleaned and descaled and then moved through the production line. Computer-controlled machinery squeezes, rolls and manipulates the blooms into a new form. In less than 10 minutes, the original bloom has a completely new cross-section profile and has been transformed from 7.5 metres to just over 108 metres in length. The rails are then pre-bent while still hot to counter the bending that occurs as they cool. Once cooled, the rails are straightened and trimmed and then passed through a complex computer-controlled NDT process to look at their profile, internal and surface quality using UV, lasers, ultrasonics and eddy currents. The tests ensure that every rail leaves the site free from defects. At Network Rail, we want the longest rails that we can practically deliver. The fewer joins, the stronger the rail. The longest rail that Tata Steel currently supplies to us is 108 metres long. So 2 rails are flashback welded together to produce a 216 metre string. This is the practical limit of what we can deliver to track. Finally, the finished rails are loaded onto a delivery train. The rails are flexible enough to negotiate bends in the line and make their journey direct to the location where they are required. The standard of rail produced by Tata Steel is very high. But even the best rails won't last forever.
My name is Brian Whitney. I'm the Principal Track Engineer for Network Rail. Part of my job is to understand how the degradation of rail occurs, how quickly it happens, where it happens, and how to mitigate against it. There's 4 main types of degradation we see with rail. There's fatigue damage on the surface and internally within the rail. There is wear, both on the head and side wear. There is also plastic deformation of the rail and a loss of section due to corrosion. There's a few examples of rail we have here. This sample here shows a fatigue crack which is initiated from the surface of the rail. It's caused by the repeated passage of wheels over the surface, which will initiate small cracks, and then through fatigue, this will grow progressively over a long period of time. The discoloration and classic markings you can see here are a result of the surface becoming oxidised and corroded where it becomes exposed to the elements. Surface damage and rolling contact fatigue is our biggest cause of problems. It accounts for something like 50 to 60% of all defects we remove from track each year. Other forms of fatigue that we see, here we have a large star crack which is originated from the bolt hole at a rail end. Equally, these are defects we need to manage. If they're allowed to go to failure, can result in a piece of the railhead becoming detached. Plastic deformation is another thing we see where the rails degrade. This is where the rails are physically deformed. They are spread, the rail steel itself is distorted and deformed under traffic. You can see the start of a small split within the middle of the web. These will propagate under traffic if not managed. They will grow to a larger size, the split will open up, and in extreme cases can result in a piece of the rail becoming detached. Most of our defects of this type occur in older rails where there are either inclusions or impurities within the rail steel which form a point of weakness which under repeated loading will cause the rail to fail. Another type of degradation is corrosion. Here we have an example of a rail removed from an aggressive environment where the foot of the rail is corroded away, a large amount of material has been lost. This will result in rail failure if the rail is not removed in good time. Aggressive areas are where we would have exposure to water or perhaps the sea on salt water. Level crossings are particularly bad where we have a lot of water from the road, and also during winter salt is applied to the road which causes a significant increase in the rate of corrosion in those locations. And finally, we have to deal with wear. This can be either vertical wear on the top of the rail or side wear you can see here from the side of the rail where the wheel wears the rail away.
One of the most important ways we manage rail is through inspection. At Network Rail, we use a fleet of monitoring trains to check on the condition of our track. Monitoring vehicles allow us to cover large quantities of rail miles in regular cycles. But in complex switch and crossing layouts, we still need to inspect on foot using portable kit.
This piece of equipment here is a Sperry roller search unit, also known as a walking stick. This is used by our ultrasonic operators who carry out a large amount of pedestrian testing in areas where we can't use vehicles to test, or in areas in lower category routes where we don't program the vehicles. The ultrasonic equipment here contains the Sperry roller search unit. This contains 9 probes which are used to scan the head and web of the rail. The floor detector, which provides the signal and response and is used to detect any defects internally in the rail. This is contained in a walking stick to make it easy to push along the rail to ensure the stick stays aligned with the rail to carry out the necessary inspections. The inspection processes that we use today, the frequencies and the techniques and technologies that we use have been developed to minimise the risk of a rail breaking, to find defects in sufficient time that we can plan their remediation. If this isn't carried out at the right frequencies, then we can end up potentially with a catastrophic accident similar to what happened in 2000 where the train derailed because of a defective rail at Hatfield.
Following inspection, the next most important part of rail management is preventative maintenance. And the principal means of preventative maintenance are grinding and lubrication. Grinding is carried out on our main lines on a regular cyclic basis. It maintains the correct shape of the rail, removes small surface imperfections, and reduces the stresses that lead to fatigue damage in the surface of the rail. We use lubrication to minimize rail wear. Track-based lubrication equipment deposits a small bead of grease onto the wheel, which is then carried around the outside bend of a curve. Lubrication is used on most tight curves on the network to reduce rail wear and the premature replacement of the rail. Eventually, however, it will be necessary to replace the rail. The primary reasons are the number or severity of defects, wear or corrosion. Some rail can last up to 40 years if on a straight piece of track, but on the curves of a high-speed line, or where the rail is affected by road salting, the lifespan can be reduced to less than a year. Typically, if a relatively short section of rail needs to be replaced, this will be done at night to minimize the disruption to traffic. In this instance, a corroded level crossing rail is being removed and replaced. The defective rail is cut out and then removed from the site using a road rail vehicle. Once clear, a replacement section which has been cut to the required length is brought in and lowered into place. This will be attached to the existing line using an aluminothermic weld. First, the rail is clamped and pulled into position, and a mould assembled around the two rail ends to be joined. The rail ends are heated before welding to prevent the rail steel becoming brittle if it is allowed to cool too quickly. A crucible is placed on the mould. It contains iron oxide with specific alloying elements and volatile aluminium powder, which causes a chemical reaction that reduces the iron oxide into steel. The chemical reaction generates a huge amount of heat that melts the constituents to form liquid steel, which pours into the mould, fusing the rails together. The mould and excess weld metal is removed while it is still hot. The stripped weld is then profiled to exactly match the rail profile and produce a smooth finish. Following inspection, the new level crossing rail is ready to be used as part of the network.
The rail management engineer continues to face a significant challenge. Modern expectations for 24/7 operation, modern vehicles, whilst safer and more comfortable, are often heavier. These all result in great amounts of rail damage. One of the ways we can help combat rail damage and deterioration is the development of new materials. A number of processes have been employed to produce traditionally harder and harder rail steels to reduce wear. Recently, we've worked with Tata to engineer a new steel which provides not only a wear resistance but also a resistance to fatigue damage. This material, HP, we've just started installation in track and utilises some clever metallurgical and chemical alloying additions to produce a strong premium grade rail steel without the need for expensive heat treatment. This provides us with a cheaper premium rail steel with a similar performance to some of the more expensive heat treated steels currently available.
Careful management of materials, their specification, production, maintenance and replacement is a crucial part of rail engineering. It allows us to maintain progress, to keep trains running safely and efficiently, no matter what the demands of traffic, line speed or location.
I hope you enjoyed that little interlude. We're going to talk about Hatfield, that accident at Hatfield, if we have time a little bit later. I just want to point out there's one problem I have with that video. I love that video, but there's one really big mistake that's in that one. And that's when they were showing the replacing of the rail. They showed them torch cutting the rail using a torch to cut the rail out. You can use a torch to cut the rail out if you come back and you use a rail saw to cut off the torch cut ends. Using a torch to cut the rail will metallurgically transform the steel and make it brittle. There are a whole history of accidents and derailments associated with just torch cutting the rail and trying to weld repair it. So you never, never, never torch cut a rail and weld it back in place. If you torch cut a rail, you have to take a rail saw and saw off the ends that were cut off and then weld in a new place. That's, there are a couple of little other things I disagree. By the way, I worked with Brian Whitney for many years. I knew him for many, many years. I always have to make that comment about the torch cutting, because you just don't torch cut rail. Okay, so the video sort of showed you the steel making process without me having to go through this. This is a chart I got from a Chinese mill, a very modern mill using old Siemens equipment that I visited on behalf of the U.S. Railway because they were looking to buy some steel a number of years ago. But you can see here, this is the continuous caster, which they showed in that shot. Again, they showed the blooms going into the continuous caster. So here are your blooms going into the continuous caster. The continuous caster then goes through a process of shaping, going through the roller heads, going through the various roller mills to get the right shape of the heads. So if you have a UIC 60, a UIC 50, and an AREA 136, they all require different roller heads. The mill has to change their heads every time they change sections. So there's a cost penalty associated with having a mill change their section size to conform it. So that's built into the price. Then you go through the various inspection stages. Here's the heat treatment stage on the outside. So you can see here, typically you have and within the rolling mill, you have your rolling lines, usually about 7 stands. You saw a cooling bed, which you saw, that's where they pre-bent the rail. Roller straighteners has strengtheners, sorry, it should be straighteners. Automatic inspection station, which they talked about, saw and drill section, and final inspection, all of which are part of the process that you saw in that abbreviated movie. Again, just some quick shots. There's a bloom entering a roller station. So this is not in the final form yet. Here's the first of 7 roller stations that'll end up putting it in the cross section of the rail that you want. Let's say you want a UIC 60, the rollers are designed to give you UIC 60 rail. There's the pre-bent rail on the cooling bed, exactly as they showed it in the movie. This is a roller straightener unit where the rail, which is right over here, is going through these rollers, which are straightening them out, because the cooling process introduces not only lateral distortion, it introduces vertical distortion. So there are both vertical and lateral roller straighteners to straighten the rail out. So you get the final straight rail you want at the end. Ultrasonic testing of rail. Here you can see the various ultrasonic probes. We're going to talk about ultrasonic testing in a later class, but you can see the various probes here that are designed to look for internal defects into the rail, final inspection, barcoding, and shipping to the customer. There's your finished rail. These are then welded together and shipped depending on the production specifications. So let's talk about a few parameters here that I want to address. I want to start off with rail hardness. We talked about rail hardness briefly. Basically, the harder the rail, the lower the wear. You heard from Brian Whitney, and I'm going to talk about failure again some more. Wear is one of the major reasons for removing rail out, particularly on curves where you have side wear of the rail. And so curved rail is very susceptible to a high level of wear. Modern standard rail has hardness is greater than 310 BHN, except for some of the lower section UIC sections, which may go down to 260 to 280. The ARIMA rail does not allow any rail to be below 310. The UIC or the EIN sections are moving in that direction, but they still allow some rails in the 280 BHN range, 280 to 300 BHN range. Intermediate hardness rail tends to be greater than 325. High strength rail, premium rail is greater than 370. Up to about 400. For all practical purposes, we don't want rail harder than 40 BHN, because what happens is you make a rail too hard, it's less ductile. It means it doesn't stretch as much, and that means it's more fracture prone. So if there's a small crack, that crack can propagate very rapidly. So because of the ductility requirement, rail is nowadays primarily between 300 and 400 BHN hardness. And there's a direct, as I said, relation, or an inverse relationship between wear rate And hardness, there's my hardness over here. And you can see the wear rate decreases rapidly. This is standard rail hardness range. This is a premium rail hardness range. This is some of the old British steel hardness range, where some of the lower level UIC steels are still also in that range as well. Okay, so how do you connect rail? So rail is generally rolled in lengths of between 12 meters and 100 meters. It used to be that the standard rail length was 39 feet, which was roughly a little bit under 13, which is a little bit under 13 meters, about 12 meters roughly. But as you saw from the movie, the modern rail is welded is rolled to longer lengths. The movie showed 108 meter long lengths of rail after rolling, but then you still have to connect them in the field. So you can connect rail either using joint bars, which is a mechanical connector, or you can use them using welding. So this is a 6-hole joint bar. Usually use 6-hole joint bars for the larger rail sections. A smaller rail section, you can get away with a 4-hole joint bar. You can see, notice, so what happens is the bars, is one bar on each side. It fits into the web of the rail between the head and the base, and then it's bolted through the web. So you have to drill holes through the web and insert these bolts and these bolts and then tighten them with the nuts. You notice the bolts are in alternate directions from left, right. That's in case there's a derailment. So if a wheel came along and sheared off these bolts will still be in place and would prevent the rails from coming apart. Again, there's a 4-hole joint bar. There's a 6-hole joint bar. Again, these are for the heavier rail sections. These are for the small rail sections. Typical cross section of a joint bar. So what you're looking at now are these two sections over here. You can see it fits into the top fillet radius and bottom fillet radius of the rail. It does not go up into the area where the wheel flanges hit. As a matter of fact, if the rail wears to the point where the wheel flange hits the joint bar, that rail has to be replaced. You cannot have the wheel flange hitting a joint bar. That's a recipe for disaster. The design of the joint bar is generally so that the moment of inertia of the two joint bars are equal to the rail section, so that in this one gap area, the joint bars have sufficient bending strength to match a rail section and they don't overstress the rail. Of course, in this zone, you have a higher moment of inertia and you have less bending and lower stresses. But in this gap between the two rails where the joint bar is, you want the stresses to be no different than what you see in normal rail. So that's a joint bar. Now, there are two broad categories of welds. The thermite weld and the electric flash butt weld. They operate very differently with very different principles. The thermite weld is the weld that you saw in the movie that they showed. That's where he put the molds around the rail. So in a thermite weld, you basically have a gap between your two rails. You put up some molds in here, and then you pour molten steel from the thermite process, which, as was indicated in the movie, is an exothermic process which generates heat. So you have this very hot molten steel pouring into this gap, filling this gap, and then you let it cool, and then you have to grind it down to match the shape of the That's the thermite weld process. The second process is the electric flash butt weld process, both mobile and plant. So there are two versions. This is a mobile head. This is a plant head. So the way the electric flash butt weld process works, we've got more space over here, is I have my two rails. Now, instead of leaving a gap and filling the gap with molten steel, what I do is I press the two rails together. In fact, I use, you can see here, these hydraulic actuators. I'm actually exerting a clamping force, pressing these two rails together, and then I'm running electric current through the rails. So I'm heating up by running electric current through the rails, applying this pressure, and then what happens is I weld this together and I actually extrude some steel. So this pressure causes some of the original rail steel to extrude outward. So I actually lose steel in an electric flash butt process. In the thermit process, I gain steel because I'm adding steel to fill the gap. In the electric flash butt welds, I'm pressing them together and then I'm extruding it. So if I'm make 20, 30 welds in a row, over that point of time, I may have lost a meter or certainly, 20, 30, 50 centimeters of rail. And then I have to replace that. I have to add that rail in at some point in time to ensure that I have enough rail for continuity. Electric flash butt welding process is more expensive, more difficult, but stronger than the thermit weld. So in order of strength, the thermit weld is the weakest. The electric flash butt weld is stronger than a thermit weld, but not quite as strong as parent rail. So pure rail. So that's why I want to roll my rail as long as possible, because rail itself is stronger than any welded joint process. But of the two welding processes, the electric flash butt weld process produces a stronger weld, a significantly stronger weld than the thermit process. But it's more difficult to apply. The electric flash butt weld machine is a very complex machine, and you don't go out and just do one or two welds. If you're going to do one or two welds, like the movie showed, they were just replacing a plug of rail, putting in a plug of rail, maybe a 10-meter plug, then you're going to have to thermit weld it in because you can't bring an electric flash butt weld machine out for that process. They're too big, too complicated, too expensive. You got to bring them out there if you're doing a large production run of welds. Okay. So let's talk a little bit about what rails can be used for. Now I'm talking about the regular T-rail. So this picture is a good example. Okay, so this is my running rail. These are my two rails, my two standard rails that my wheel goes on. We'll be spending most of our class talking about that. This rail in between is a guardrail. The purpose of the guardrail is to do absolutely nothing in normal traffic. The guardrail, as you can see, is nowhere near where the wheels are. And if everything is normal, the guardrail does nothing. The purpose of the guardrail is an emergency. If there's a derailment and I want to keep my rail vehicle from falling off of a bridge or falling off of an elevated structure, I have a guardrail which will catch the wheel flange as if the vehicle is trying to slide in this direction, this guardrail will catch this wheel flange and keep that rail in place. If you go look on a typical bridge in Israel railways, for example, you'll see your two running rails, and then you'll see two guardrails in the center of the track, well away from the running rails, but each designed to catch one of the wheels. So, if it tries to go off the bridge in this direction, if it tries to go off the bridge in this direction, one of these guardrails will catch a wheel and keep the vehicle from going off the track. So that's my guardrail. Now I have a third type of rail, which is this one right over here, which is the restraining rail. So this rail is my running rail. This is where my wheel is. So envision my wheel flange looking like this. Let's change the color a little bit so we can make it easier to see. So envision my wheel flange looking like that, running on this rail. Now I have a mating wheel flange that runs over here. that's generating lateral lateral load, of course, because it's going around the curve like we talked about. In very sharp curves, particularly very sharp metro curves, where you have curves that have a radius of less than 200 meters, or in some cases, a radius less than 100 meters. So in that case, you're generating extremely high lateral forces, and you're concerned about overturning this rail or climbing that wheel. So what you want to do is you want to pick up part of that lateral load at the low rail. You don't want all that low rail to go, all that lateral load to go into the high rail, to go into the low rail. So you put in this restraining rail. So if I have my wheel, my running rail is over here on the low side. And you can see if I'm going over here, I'm really not picking up a lot of lateral loads. But if I put in a restraining rail over on the outside, which is right over here, then you can see this will pick up now part of my lateral loads. And what the purpose of the restraining rail is to split the lateral load between the high rail and the restraining rail, so you don't see an excessively large load into the high rail. And this is something you'll see primarily in metros, particularly heavy rail metros with very sharp curves. So if I have a very, you'll also sometimes see them in very sharp curves in railroads as well. Question?
Yes, I have a question, please. You're right. We have it in Tel Aviv. There are less than 150. I have to put this. Chinese said the guardrail would be also okay. And my question is, why at all we need this guardrail if you want to prevent the derailment, not training?
Right. The only purpose of a guardrail is to prevent a derailment. A guardrail is not designed to do anything in normal operation. A restraining
rail prevent something.
You're breaking up a bit. You're breaking up. Yeah, I can't,
because it's too far away from main rail. No?
What, the guardrail? You're talking about the
guardrail is not preventing from derailment, isn't it?
No, the guardrail is preventing from derailment. So what happens with the guardrail? So let's look over here. Here are my two running rails. And let's put a guardrail in the middle. Okay? So in normal operations, I have a wheel here and I have a wheel here, and the guardrail sees nothing. You know, the axle's up here, the guardrail sees nothing. In the event of a derailment, what's going to happen is, let's say this wheel climbs over. So all of a sudden this wheel, so the whole bogie is moving this way. So what's going to happen is that this wheel over here will hit the guardrail, and this guardrail will stop this bogie from moving off the track. It will not.
The check rail from the right will prevent. Then why we need the guardrail from the left?
Okay, well, first of all, you in most railway applications, you don't have a restraining rail. Okay, so if you go look at Israel Railways, and you go down their bridges, look at any bridge on Israel Railways, there are no.
About the bridge, I'm talking about the tunnel.
Okay, so in a tunnel, if you have a restraining rail, you don't necessarily need a guardrail, but sometimes you're a little bit nervous that this wheel flange will pop out. Okay, mm-hmm. If there's an excessive level of loading on this wheel over here, there's a possibility that this wheel can pop out of the restraining rail. And if it pops out of the restraining rail, there's nothing to keep it from derailing unless there's a separate guardrail. And that's why there's a guardrail here. And you notice there's only one guardrail. So this guardrail is only designed to be looking in this direction.
And here it's because of bridge.
Yeah, again, you notice from this picture, this is an elevated structure. In a tunnel, you're a little bit less concerned because then you can hit the wall. And although that's going to cause damage to the vehicle, it's not going to cause the vehicle to fall down 10 meters or 20 meters or 50 meters.
Yes. So actually the logic to do in tunnel check rail and not the guardrail.
Yeah,
I mean the restraining rail and not the guardrail.
that's correct. Because ultimately you have the tunnel wall if you want to argue that.
Okay, thank you.
Okay. So now we can start talking about the rail stress environment. The rail stress environment is an extremely complex environment. And while we already spent a little bit of time talking about bending stresses, and we're going to come back to bending stresses here, we actually have bending stresses, contact stresses, and longitudinal stresses all present. As I said in an earlier lecture, bending stresses is used primarily heavily in the design process. But when I'm dealing with maintenance, I need to deal with my entire stress environment, my bending stress, my contact stress, and my longitudinal stress. And as Brian Whitney pointed out in the movie, you have fatigue-related problems, both surface and subsurface fatigues. You have wear-related problems. He talked about corrosion problems, which you have if you have a lot of water present, such as metro tunnels will have corrosion problems. And you probably have some corrosion problems on coastal lines. So again, the Haifa line that runs along the Mediterranean will have corrosion problems. And you'll also have pull-apart problems, which he didn't talk about, but which we did talk about. We talked about thermal loading. Okay.
When you talk about water problems, it's because of stray current, isn't it?
Yes. The biggest problem is with stray current, but you can also have a problem without stray current if you have a water with a high salt content, seawater. Seawater is very corrosive by itself. So
clear, but it also make bigger the stray current if it's salty.
Yes, and it's even worse. So if you're using, okay, so in a lot of metros, the most metro designs, the ground return is the running rail. So you now have this big, you have a ground return current in your running rail. And then if you're sitting in water at the same time, you have an electrolytic process. So this whole stray current problem is a real problem for corrosion. But you can also have corrosion even if you had diesel power on coastal lines. So we see railroads that are not electrified, but are near salt waters, near oceans or near seas, where there's a very heavy, a lot of seawater or a lot of sea mist going down there, and that will also develop corrosion problems.
Yeah.
And so those problems do exist, and we'll talk about those problems a little bit later. But right now, I want to talk a little bit about stresses. So the big three stresses that the rail sees are the bending stress, the contact stress, and the thermal stress. We've briefly talked about bending stress. We briefly talked about thermal stress. We didn't talk much about contact stress, which we will. Now take a look through here. This is my cross-section of my rail. My bending stress has typical bending stress distribution. So there's no stress at the neutral axis. And then there's either there's maximum tension and maximum compression. Underneath the wheel, it's maximum tension on the base and maximum compression in the head. In the reverse moment zone, it reverses. So I have tension in the head and compression in the base. And so it takes this form. My thermal stress is uniform. My thermal stress is uniform across the cross-sectional area. It's nothing more than my thermal force divided by the cross-sectional area, and it's constant. My contact stress is right where the wheel is. And my contact stress is very local, very high at the wheel rail interface, rapidly dissipating so that by the time I'm about halfway down the railhead, my contact stress virtually disappears. And I have no contact stress effects anywhere below the middle of the railhead. So again, just another way of looking at it. My contact stresses affect rail wear, head wear. They affect fatigue, shelling, rail fatigue and surface fatigue. They affect formation of plastic zone. My plastic zone in the railhead, with Brian showed just briefly, and I'll show some more, is associated with the contact stress. And by the way, these are often the very largest stresses that you see. Bending stresses, of course, vary with the section of the rail and the dynamic load level, and they affect fatigue life as well. Thermal stress is associated with the thermal strain change, with temperature change, the delta T that we talked about previously. And again, it contributes, not only does it contribute to buckling and pull aparts, it also is additive in the fatigue environment as well. Okay, so let's talk a little bit about contact stress. This is good wheel rail contact stress. And by the way, please never try to take a picture like this, ever. I treasure these type of pictures because the guys who went down to take these, but a lot of these pictures were taken actually by remote cameras. So remote cameras are much more effective. You just don't want to try to go down there and take a picture. This is good normal tangent contact stress. You notice there's a gap between the flange of the wheel and the rail, which is what it should be when you're running down straight track. All of my stresses are right in this zone. There's an elliptical zone, which is my contact zone, and that's where all my stresses are. This is a photoelastic slide. So this slide was taken of a photo using photoelastic material, modeling the stresses at the wheel and the rail. By the way, you notice this, you see the same stress distribution in the wheel as in the rail. Wheel steel is very similar to rail steel. In fact, there's a running argument about which should be harder, the wheel or the rail. Most of the time, it's the rail is made harder because it's easier to change wheels out than it is to change rail out. Changing rail out is a more expensive process. You can see here in a photoelastic model, the number of color bands determines the amount of stress. The stress here you can see is down the center of the railhead. There's a lot of unstressed steel around it, so that even if I went plastic, it can't deform anywhere. We'll come back to this plastic deformation a little bit later. But this is good centralized normal wheel rail contact. So what happens when I go around the curve? When I go around the curve in this particular case, my axle is shifting towards the outside or the high rail. So this is a new wheel, new rail flanging. And you can see I have this contact zone here all of a sudden. Here I have separation, I only have contact here, but here I have high contact on the high rail or the outside rail of the curve. My contact can take a couple of different forms depending on the condition of the wheel and the rail. whether I have new wheel, new rail, worn wheel, new rail, worn rail, new wheel, or worn wheel, worn rail. The contact shape is different, but the two broad categories of wheel rail contact are 2-point contact and 1-point contact. So this is 2-point contact. 2-point contact is exactly what it says. I have one contact point between the wheel and the rail on the tread of the wheel, top of the railhead, and I have a second contact point on the flange of the wheel, side of the railhead. So you can see this is what could give me very rapid wear down here on the side of my railhead. I can also have 1-point contact where okay, so one of the things that happens here, by the way, is my lateral and vertical load. Let me get a different color so I can draw on this a little bit better. So I have a lateral load here and a small vertical component here, and I have a vertical load here and a small lateral component over here due to the coefficient of friction. With 1-point contact, my vertical and lateral loads all go through this 1 point. So I have the highest amount of contact stresses. So when I have this type of conformal contact, when the wheel and the rail wear into each other, then I can have all my loads and all going into this 1 point, generating very high stresses.
Actually, you say it's okay when it's 2 points?
Yes.
But why this happens on curves? Because when it's new and you said it's fine, it's 1 point.
Actually, it's not fine 1 point. It all depends on your load level. We're going to talk about fatigue failure in a little bit. But with 1-point contact, with these very high contact stresses, you develop fatigue defects in this zone.
But if it's about in the middle, then it's fine.
What do you mean in the middle?
From above, in the middle of the, yeah,
It's over here?
like this, yeah.
This is perfect. The problem is you can't get this on a sharp curve. This is impossible on a sharp curve, because in a sharp curve, you're going to flange. Even on a medium.
So we're talking now about curve only.
Medium to sharp curves, exactly.
Okay.
So in medium to sharp curves, yes. So in straight track, you should be doing this. This is what you should look like on straight track, and you should not have a problem with 1-point contact. The contact should always be over here. On shallow curves, where you can use the conicity of the wheel set to steer around the curves, you should still be able to maintain this gap and have the center contact. But once you get to medium to sharp curves, you start to flange. And once you start to flange, you have contact. So your choice is a 2-point contact versus 1-point contact. And the answer as to which is better is it depends. This is a case where you really have to match your contact with your loading condition. So heavy freight railroads do not want 1-point contact because the stresses are so high, they're going to generate defects. So what they're going to come along and they're going to grind the rail. They're actually going to grind off this piece of the rail. And we'll talk about rail grinders a little bit, but you saw very briefly, you saw a picture of a rail grinder in that movie, that the Network Rail movie. They're going to grind off that rail and they're going to force 2-point contact. Because by forcing 2-point contacts, they distribute the load and they reduce the level of stresses. In metros, where the load level is a little bit lower, you sometimes will sometimes will prefer 1-point contact, because in 2-point contact, you're basically trying to go around the curve with 2 different contact points. this is actually going to generate a slightly higher lateral load. So for a lower load environment, such as metros, sometimes a one-point contact is more desirable. And so what you would tend to do in this type of case, and we'll talk about this a little bit more when we talk about profiling, but what you're going to tend to do is you're going to try to get a distributed contact that looks like this. And that would spread the load a little bit, but still not have the very high contact stress. But for very heavy load environments, this is no good because this generates very rapidly fatigue defects. And I'll show you examples of that. If not today, then tomorrow. We won't get to it today. So you can see here the photoelastic slide showing, you notice how much larger the number of color bands I have here, showing the much higher contact stress. Now, the third contact case we have is what happens when the wheel wears. And when a wheel wears, it wears like this. So a normal wheel, we have good contact. We want to have contact in the center. But as the wheel wears and it wears off the center, we start having contact on the outside. So when we start having contact, now you can see here, this warm wheel. Here, I'm still running in the center. But let's say I go around the curve. Let's say my curve is forcing me out in that direction. I can start moving this point over here and I start getting contact. This is contact on the field side of the rail. So this is my gauge side. This is my field side. And this is, by the way, one of my field tricks. I like to use a can of spray paint. Spray paint the rail before a wheel goes by and let a train go by and see where the wheel is. And you can see here that the wheel, most of the wheel contact was here on the field side, which means I have this situation. I have this contact between this field side of my wheel and the field side of my rail, which was the third case, by the way, I gave you, which is a high overturning moment, a low overturning resistance. But also notice that in addition to the high contact stresses here, all of a sudden I'm seeing stresses over here that I hadn't seen before. In my previous contacts, my stresses here were very, very, very minor. And my stresses here are very, very, very minor. In this case, my stresses here and here are very high. And in fact, I have a whole class of defects called head and web separation that initiate right at this if I have improper loading. So controlling the location of the load and the contact point of the load becomes very, very important in rail maintenance. And in fact, one of the major technologies that developed in the last 25 to 30 years and which contributed to that extension in rail life that I showed you between 1980 and 2010 is the development of mechanisms to control the wheel rail contact point and to improve wheel rail contact. So for example, Israel Railways just spent, I forget how many, I think 25 million euros to buy a new rail grinder, which is specifically designed to control the wheel rail contact. And in fact, I think 2 years ago, pre-corona, I was over there giving a course on how to do profile grinding to control wheel rail contact for Israel Rail. So what we're doing here is we're trying to look at the wheel rail contact stress. So wheel rail contact stress, which is everything we've been showing you up until now. This is my wheel rail contact stress. It's usually defined using Hertzian contact stress theory. Hertzian contact stress theory is the most commonly used theory for wheel-rail contact. It's directly related to the local interface geometry between the wheel and the rail, to include, among other things, the radius of the top head of the rail, the radius of the wheel, the radius of the transition zones in the rail. All of this directly relates to the shape and size and magnitude of the wheel-rail contact zone, which in turn affects the magnitude of the stress. And so contact can be central on the rail head. It can be two-point contact, which includes wheel flange contact on the side of the rail head, and then contact in the gauge corner of the rail, all of which we've talked about. So there's my central contact. There's my, this is actually a 1-point contact where I'm contacting at the flange root gauge corner of the rail, and then the field contact we showed. Okay, so contact stresses are local to the surface of rail. So if this is my rail and I plot my contact stresses fall off very rapidly. And they're actually related, as I said, to the shape and profile of the rail. So Hertzian contact stress theory assumes contact between two cylinders. D2, has a radius 2, and D1 has a radius 1. So typically this is the rail. And this is the wheel. And there are a whole bunch of analyses, which I am not going to go through Hertzian contact stress theory. And rather, I'm going to give you the most simplistic of the analyses. So in the most simplistic of the analyses, the contact zone between the wheel and the rail is elliptical. Which means it has the shape of ellipse with a major axis of 2A and a minor axis of 2B. And so, okay, before we go further, now the area of ellipse, which I'm sure you all remember, is pi AB. And just to make it easier for you to remember, if you take the limiting case where this goes to a circle with a radius r, then A to A equals B equals R, and the area is pi r squared. And I know you all remember that area of the circle. So the area of ellipse is pi AB. The average contact stress, therefore, is P over A, where P is my vertical dynamic wheel load. Emphasis on the word dynamic. So if I give you a speed, use the ARIMA formula and calculate me a dynamic load. The area, as I said, is pi AB. That's the average contact stress. But the distribution of stress across the ellipse is not uniform. It's non-uniform, and the maximum contact stress, which is as the center, is 3/2 P over A, or 3P times 2 pi AB, where again, A is the, or 2A is the semi-major axis, and 2B is the semi-minor axis. Now, if you want to calculate 2A from Hertzian contact stress theory, you can use this equation over here, where 2A is equal to the vertical load times the wheel radius times 2 times the, or 2b, which is the semi-minor axis, the width, times the modulus of elasticity, all raised to the 0.5 power. For the most part, I'm going to basically be giving you A and B's. I'm not going to really be getting into a lot of Hertzian contact stress theory for this class. This is, by the way, this is normal stress. Remember normal stress? So normal stress is a stress perpendicular to the surface. I also have a shear stress, and my maximum shear stress is 0.3 times my normal stress. So again, if I can calculate 2A, so in this particular case, let's say 2A is 13.5 millimeters, 2B is 18 millimeters, the area is pi AB, which is 190.85 millimeters, and then my stress is 3P, my average stress is P over pi AB. So if my wheel load is 160 kilonewtons divided by 190.85 millimeters squared, and that'll give me my normal, my average stress. My maximum stress is 1.5 times that, 3.2 times that. So again, 160 over 191 gives me 838 millipascals for my average pressure, contact stress. My maximum stress is 1.5 times that, or 1,250. Typically, for most cases, I usually want to keep my sigma, my stresses below 50% ultimate. So if you remember, I'm sure you remember everything I told you without going back through the notes. If you remember, the ultimate stress of standard rail steel is about 1,180 megapascals. So half of that is about 590 megapascals. If you remember, sigma yield is somewhere around 800 megapascals. So you can see my average pressure is right at my yield stress. And my maximum pressure is above my yield stress, even though significantly below my ultimate stress. So you can see that when the contact stress zone we're working in is usually out already at the edge of the elastic into the plastic zone, which means I'm subject to potentially for plastic deformation in my rail. This is, of course, the vertical stress. Is everybody clear about what I've done here? Let me stop for a second and just ask if everybody's clear here. Any questions? Hopefully, I've done nothing more than basically P over A. But A is my ellipse shape of my contact zone. So I just wanted to point out to you just how high the contact stresses are from Hertzian contact stress. So again, this is a normal contact stress. If I want the longitudinal, so if I want the longitudinal component of my contact stress, my longitudinal component of the contact stress is between 0.3 and 0.8 times the normal stress. So why do I want the longitudinal component of my contact stress? The longitudinal component of my contact stress is what I add to my bending and my thermal stress. So if I go back I'm going back too far. Oops. If I go back here, if I want to add this contact stress to my bending and my thermal stress, I need the longitudinal component. It's no longer the Hertzian contact stress. The Hertzian contact stress now is in the down direction. So my longitudinal component is between 0.3 and 0.8. For most elastic plastic behavior, it's about 0.3. So 0.3 C sigma C, so sigma sub C max. So if my stress is 1257 megapascals sigma sub C max, my longitudinal component of the contact stress is 377 megapascals. And just to give you an example, so this comes out of some finite element modeling of the rail. So these are my stresses in the various orientations. So first of all, this is the rail stress 5 millimeters below the running surface of the rail for an elastic material. So for rail, before it's going to go on any work hardening, any plastic hardening. Okay. So 5 millimeters below the running surface is just below the running surface of the rail, where the contact stresses are very dominant. You can see my vertical stress is this purple. My longitudinal stress is this horizontal. My transverse stress, which is in this plane, is the green, and these are my 3 shear stresses. If I go 13 millimeters below the running surface of the rail, so look over here, my normal stress is about 900 megapascals in this example, right? If I take the exact same model and go from 5 millimeters to 1300 millimeters, my 900 drops to about 300. So you can see how quickly it falls off. And by the time I get to about 25 millimeters below the rail, it's probably, see, do I have another one? Yeah, it's 20 millimeters below the rail. It's about 150 megapascals. So you can see how quickly it dies off. By the time I get to 30 millimeters below the head of the rail, there's basically no significant contact stresses. Now, I also have a shear stress, though. So I have normal stress, I have transverse stress, longitudinal stress coming out of the page. I have transverse stress, and then I have shear stress. Remember shear stress? Shear stress is what causes the distortion of an element. My shear stress behaves slightly different. My normal stress is maximum at the top and then quickly drops off. My shear stress actually in Hertzian contact stress theory is maximum about 4 millimeters below the surface of the rail and then drops off. So it's high, increases, and then drops off. So my maximum Hertzian shear stress is 4 millimeters from the top of the rail. My maximum Hertzian normal stress is right at the top of the rail. This is going to come into play a little bit later when we talk about defects. So this actually shows you normal stress versus shear stress. Again, normal stress is maximum. This is vertical. This is longitudinal or radial. So you can see how quickly it falls down. But the maximum is at the top. Here, the maximum is about 4 millimeters below the top of the rail. Okay, so let me recap this a little bit so you can understand what I'm looking for here. Oh, I don't want yellow. I can barely see yellow. Okay, so my Hertzian contact stress, sigma sub c, is equal to P, my dynamic wheel load, as we've solved in the class examples, as we've gone over the class, divided by the area of the ellipse, the contact ellipse, pi AB. That's the average contact stress. The maximum contact stress is 3/2 mean, 3/2 average, or 3p over 2 times the area. So this stress is my normal or my vertical stress. If I want my longitudinal contact stress, so this is my rail. If I want my longitudinal contact stress, my longitudinal contact stress longitudinal is equal to 0.3 times sigma sub c. Okay. Now bending stress, I'm just going to quickly review because we've already gone through this one previously, but I just want you to refresh your memory. Rail bending stress is exactly from the beam and elastic foundation theory. Back to my highlighter. The moment is P over 4 beta, eta minus beta x cosine beta x minus sine beta x. If I have one axle, the maximum moment is under the wheel. If I have two axles, I have to use superposition and solve it. My stress is MC over I. That's the stress at the base. If this is C, that's MC over I. The stress on top here is M H minus C over I, because this distance is the total height minus C, and beta is the 4th root of K over 4EI. And these are all tabulated for you. So the bending stress is a function of the foundation system, a stiffness. Under the wheel, I'm in tension in the base, in compression in the head, in the reverse zone. I'm compression in the head, tension in the base. By the way, does anybody want to tell me what happens to my stress as the rail wears? Come on. What happens if my rail wears? What happens to my moment of inertia when my rail wears?
It decreases.
It what?
It
Say again?
decreases.
It decreases, yes. My moment of inertia decreases as the rail wears. So if my moment of inertia decreases, what happens to my stresses?
Increases.
Obviously. My stress is MC over I. So if my moment of inertia decreases, my stresses increases. So as my rail,
But the area of contact is increases, no?
okay, and I was talking about bending stress now.
Okay.
But what happens is your area of contact as you wear and as the rail flattens, your area of contact does increase. Yes. So let's do an example for bending stress just to go through along. I have a 90-ton wagon on 4 axles. So I have 22.5 axle loads going at 80 kilometers per hour. My modulus is 6.9 megapascals, UIC 60 rail. I want to do the problem with 1 axle, and I want to calculate my maximum stress. So this is the case that we already did, we've done before. 90-ton axle, static load is 110 kilonewtons. I use my ARIMA formula to calculate my dynamic load of 160 kilonewtons. I know my I and my E from UIC 60 rail together with my C and my H. My K is 6.9 megapascals. My beta is the 4th root of K over 4 EI, which is 0.00007 over millimeter. And my maximum moment is 55 Newton millimeters, 55 million Newton millimeters, or 55 kilonewton meters. I can then calculate my stress. Stress at the base, 140 megapascals tension. Stress at the head, 166 megapascals compression. If I wanted to calculate the bending stress in the uplift zone, can go back here, find my maximum moment, which is actually somewhere in here, my maximum reverse moment. So my maximum reverse moment happens at 2.2 meters or 2,200 millimeters. It's minus 11.5 kilonewton meters. And so my stress at the base is 30.6 megapascals compression, and my stress at the head is about 34 megapascals tension. Again, I flip my sign. So I plot my stress. This is at the base. So this is tension here. This is compression here. Everybody clear on how you do that? You did the moments as a class example, and you should be able to do the stresses. There's another problem for you to work through, by the way, after this class that has to do with the load distribution as well as the stresses. So you can start looking at the next couple of problems that I gave you. Any questions? Okay, longitudinal forces. We really trying to focus on thermal forces. So the thermal force is E, A, alpha, delta T. Well, delta T is the change between the rail temperature and the force-free temperature and neutral temperature. Alpha is the coefficient of thermal expansion. E is modulus of elasticity for rail steel, and A is the cross-sectional area, except if you're calculating the stress, the longitudinal stress, it's nothing more than F over A. So the A cancels out. And so the longitudinal stress is simply E alpha delta T. Temperature. So simple example, if the force-free temperature is 10 degrees C, the air temperature is 43 degrees C, the rail temperature is 65 degrees C. My delta T is then 65.5, take away 10, or 55 degrees C. The force is 959 kilonewtons, and the stress is 131 megapascals. So again, the stress is nothing more than E alpha delta T, where delta T is 55.5. Alpha is the coefficient of thermal expansion, which I've given you before. It's actually right over here. And E is the modulus of elasticity of rail steel. And I'm not going to go through a second example. In the interest of time, I'm going to sort of skip at the moment the setting of rail temperatures, laying temperatures. I'm going to save that for the CWR class when we talk about CWR. But for all practical purposes, if you need to set your range of laying temperatures, there's a very efficient formula that's developed by ARIMA, which calculates the minimum and maximum temperature. So it gives you the range as a function of the hottest day of the year, hottest temperature, hottest rail temperature, and the lowest rail temperature. And it's basically 2 times the highest rail temperature. The minimum is 2 times the highest rail temperature plus the lowest rail temperature over 3 plus 10. And the maximum is 2H plus L sub T over 3 plus 25. This whole thing plus 5. I'm going to come back to this, but I want to get through stresses first before I get through thermal stresses. So, okay. So now this becomes fairly important. I have 3 stresses. I have my bending stress. I have my contact stress. And I have my thermal stress. Each have different characteristics. Now, if I look at my bending stress, or I look at my bending moment or my bending stress, I actually have a maximum stress under the wheel. Oops. A maximum stress under the wheel, and then I have a maximum reverse moment stress, right? We went over that. And under the wheel, if I look at my load in the head, it's compression here and tension here. So if I want to combine my stresses, and I want to look at right underneath the wheel where the wheel and the rail contact each other. So this is my maximum stress point, right? I have my wheel and my rail contacts each other. I have my maximum contact stress at that point. I have my compressive bending stress, and I have my thermal stress. all three components are present. If I'm under the wheel and I want to now combine my stresses at the base of the rail, do I have all three stresses present? Anybody?
No, you don't have the bending stress.
No, you have the bending.
Contact stress.
That's correct. You meant to say contact stress, I know.
Yeah.
Exactly. The contact stress rapidly, again, the contact stress rapidly phases out and when you're dealing with the rail. It's really significant at the head of the rail. And by the time you get, you saw the example I gave you, by the time you get about 25, 30 millimeters below the top of the railhead, it disappears. It doesn't exist anymore.
Don't you have contact stress from the sleepers?
Say again, I didn't hear the question.
Don't we have the contact stresses from the sleepers?
From the vehicle?
From the sleepers.
I don't understand the word. On the what?
He says sleepers.
Oh, no, no, those stresses are negligible.
I mean from here.
On the sleepers, no, yes, no, they're negligible. If you go through and you calculate those stress numbers, they're of the order of let's look at some of our numbers. Okay, so if we go back to our contact stress, my contact stresses are of the order of 900 megapascals here, vertically. And so 30% of that would be 0.3 times that would be roughly 270, 300 megapascals. My stresses at the bottom of the sleeper are about a tenth of that. Or less. So there's a very small contributor of it. And so by the time I take the longitudinal component, it's relatively small and it's for all practical purposes not significant. But they are present. They're important for the sleeper. They're very important for the sleeper because the strength of the sleeper is a lot less. Okay, where was I? Okay. Now, if I go look at my reverse moment zone, so my wheel is over here, and I have a reverse moment zone here. Do I have my bending stress, I have my thermal stress. Do I have a wheel contact stress here? Anybody? My wheel is over here.
No, you don't have it.
Right. I don't have it over here. This is 2 meters in front of my wheel. So I don't have any contact stresses in my reverse moment zone. So I only have my thermal and bending. So when I'm combining the 3 stresses, I only really have stresses to combine at the head of the rail, underneath the wheel. Everywhere else I don't really have. So let's do an example just to show you how that works. So if my contact stress is of the order of 1200 megapascals vertically, that's what I get from my P over A. Then the longitudinal component is 0.3 times that, is 377 megapascals compression. My bending stress on the top of the railhead, we just showed you an example, is 166 megapascals compression. And let's say for a moment, it's a very cold day. And so this was the second case that I didn't do, where the rail temperature is below the ambient temperature, so I'm in tension, and I have 103 megapascals tension. So directly under the wheel, I have my minus 377 contact stresses, my minus 166 bending stresses, and my plus 1/3 thermal stresses. So I have a total of 440 megapascals. All three are in play. If I'm under the wheel, I'm looking at the rail base. My contact stress is negligible. I'm neglecting the stresses due to the sleeper, which are small, spread over a much larger area. The bending stress is now 147 megapascals tension, because it's in tension under the rail, and the longitudinal stress is still 103 megapascals tension. So it's 0 for my contact test, plus 147 megapascals for my tensile bending stress, and plus 103 megapascals for a total of 250 megapascals in tension on the base of the rail. If I look in the reverse moment zone, so my wheel's here, and I'm over here, my contact stress is negligible. My bending stress is about 20% of the bending stress under the wheel, so it's about 34 megapascals. And it's going to be tension in the head of the rail because my moment is reversed, right? So it's tension in the head of the rail. My thermal stress hasn't changed. My thermal stress here, 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 10 meters down, 20 meters down, doesn't change. It's all 103 megapascals tension. It's only a function of the delta T. And so my tension in the head of the rail in the reverse moment zone is plus 34 megapascals, plus 103 megapascals, or plus 137 megapascals. And if I look in the reverse zone at the base of the rail, so now I'm coming down here at the base of the rail where I know I'm in compression. Again, my contact stress is negligible. My bending stress is minus 31 megapascals. My longitudinal stress is still the same. You notice my longitudinal stresses have not changed in any of these cases here. So it's 103 minus 31 or 72 megapascals. Okay, I'm probably going to stop here and just make sure you understand this, because how you combine stresses is very important. Because when we start dealing with fatigue and we start dealing with failure, you have to be able to understand how to combine the stresses. So I want to make sure you understand that. So if there are any questions, please speak now.
Yes, I have a question. When you combine stresses, what are the percentage between the contact, bending, and thermal stresses
It varies.
at average?
No, it's going to vary significantly. It can vary significantly. Like this is a good type of number. Typically the contact stress, and remember, this is the longitudinal component of the P over A term, right? Remember, we're doing that. So the longitudinal component of the P over A term is generally of the order of, again, depending on your dynamic wheel load, is between 250 and 450, 500 megapascals, okay? So if I had a very heavy axle load freight locomotive going at 100 kilometers per hour, it would probably be up there in the 450 to 500 megapascal range. If I have a light rail transit vehicle going at 60 kilometers per hour, it would probably be in the 250 to 300 megapascal range. Okay, bending stress at the head of the rail is going to be between 100 and 200 megapascals. So it's roughly going to be about half the size of the longitudinal longitudinal component of the contact stress. So in rough terms, it's going to be about half, plus or minus. The
Okay.
thermal stress is going to vary completely depending on your temperature. If the neutral temperature is 40 and your rail temperature is 50, your thermal stress is going to be, 5-10 megapascals. If your thermal stress is 40 and your rail temperature is is 0, for example, then your longitudinal stress is going to be 100 megapascals. So it's not going to really be more than about 100. The largest longitudinal stress is probably going to be about 100, 125 megapascals. So in general, in sort of waving my hands and knowing it varies greatly depending on the vehicle I'm using and the speed I'm traveling and the temperature change, etc. My largest component is the contact stress at the head of the rail, and that's going to be, maybe between 30 and 40%, maybe a little bit higher than that. And then the bending stress is going to be between 20 and 30%, and the thermal press is going to be of the order of maybe 20%, 25% as well. But I'm waving my hands a lot because it's going to vary depending on the wheel load, the speed, the track modulus, the neutral temperature, the actual air temperature or rail temperature. All of those are going to affect the relative ratios of those.
And the thermal stress can be positive and can be negative.
Absolutely, absolutely. If the thermal stress, if the rail temperature is above the neutral temperature, then you're in compression. If the rail temperature is below the neutral temperature, then you're in tension. And it could be, you can be 50 degrees above, you can be 50 degrees below. Even though the way most people do it, you're going to usually be higher below, so you're going to have more tension.
Yeah. Okay. Thank you.
Okay. I'm out of time. Try doing you got two problems I'd like to go do on your own. One is the distribution of force problems, which I don't think you did. And then there should be some rail stress problems you can start working on. If you come to a fatigue portion of it, don't worry about it, but the rail stress problems you should be doing, because you should now be able to figure out the contact bending and thermal stress loads in the rail. Okay, I have no time. I'll tell you why this is really important next week. Maybe next week we'll start off talking a little bit about the Hatfield derailment and why what I'm talking about here is very, 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 very important. And by the way, those of you who work in the metro industry and says our rail stresses are much low, we don't have any rail problems. I was called into a derailment at Washington Metro here about 1.5 years ago, which was a broken rail derailment under a metro train in Washington, D.C. So trust me, metros have broken rail derailments too. Okay. I hope you feel free to review it as soon as I get the recording. I'll try to get it posted onto Moodle so you can look this over again. Again, the slides are also on Moodle, but I'll have a recording of the session on Moodle. And again, we'll meet you next week. Okay, you're breaking up on me. I can't quite hear the question, so try it again. Repeat the question, please.
I think it only was background noises.
Say again?
It was
It wasn't any
background
question,
noises.
it was a mistake.
What was a mistake?
It wasn't any question.
Oh, okay, sorry. Okay. All right, so we'll see you all next week. you can see there's a lot of material we have to cover. There's a lot of interesting stuff that goes on in this field. Okay, everybody have a good week. Shavua Tov. And
Thank you.
we'll see you all.
Thank you.